Right, well, hi everybody. This is a talk entitled A Second Time Around Barnard Star. I did a once around Barnard Star before, but things have changed. One of the things I like about astronomy is that it is a dynamic science that we are learning more all the time. And so I thought it was time that we had a bit of an update on this one. So let's go. Well, just for a recap, Barnard's star lives in a constellation called Ophiuchus, which is the 13th constellation of the zodiac through which the planets pass. That's kind of by the by, but it's a little faint star, just as shown on the diagram there, below Hercules in the outer reaches of this rather obscure constellation, Ophiuchus. It's named Barnard's star after this guy, Edward Emerson Barnard, an American astronomer who actually has been responsible for a terrific number of interesting objects being found all over the sky, lots of nebulae, but in particular, this star bears his name. So what's special about it? Well, actually, not very much in some ways. It's a red dwarf star, and red dwarf stars make up something like 70% of all stars. So this is pretty typical. Red dwarf stars classified class M, and this is an M4, so it's in the middle of the 0 to 9 range that you have for an M class star. So again, fairly middle of the road sort of red dwarf. Temperature 3,200, that classic red color because of the low temperature, the sun being much hotter at 5,800. 16% of the mass, the smallest red dwarf you can possibly have is around about 7.5 to 8% of the mass. So this is a little larger than the smallest end of things, but such small stars running at lower temperatures produce a heck of a lot less by way of output. And this one is 1/25,000th of the total power output of the sun. So no wonder it's really quite hard to see. It spins on its axis in about 142 days, plus or minus, and there are a lot of stellar flares on it. The artist's impression on the right is trying to show some of those. But it seems to have gone into a quiet phase as regards flares and sunspots since about 2005, possibly rather like the sun did in the Maunder minimum and the little ice age that we had on Earth when we had frost fairs on the River Thames and all sorts of other effects across the world. Now, as I say, it is quite a small star. These red dwarf stars are barely larger than a gas giant. There's Jupiter and Barnard's star to scale, so it's maybe nearly double the radius. Well, that would give it 8 times the volume if it was, you do the maths because of the cube law to get volume. So there's a certain amount of mass there, but it's still very much smaller than the sun. And I said there are 76% of all stars are red dwarfs. That's what this diagram is trying to show. And if you actually add in the sort of lower mass K type stars, then you really get up to the vast majority being these dwarf stars smaller than the sun. And really the stars that are larger than the sun are just in that top 3.5%, the F, A, and B and O class stars. So it's just absolutely one of the most typical. Now, if you plot things on the good old Hertzsprung-Russell diagram showing luminosity against temperature, then you can see Barnard's star is marked down there, down to the bottom right, and it's not quite at the bottom of the list. There are some that are smaller, but it's a very ancient star indeed. We think it formed about 10 billion years ago, twice as long ago as the sun, and almost all the way back to the Big Bang itself, the universe being 13.75 billion years old or so. 10 billion years means this is a survivor from relatively early times. Must have been one of the first stars to form in the Milky Way galaxy in the grand scheme of things. And as such, it's quite low in heavy elements. The carbon, oxygen, iron, all those sorts of elements that are cooked up in the center of giant stars didn't really have very many generations before Barnard star formed out of the available material, and so it didn't pick up the signature of previous generations of large stars having polluted the universe with their so-called metals. Astronomers call anything heavier than helium a metal, much to the annoyance of chemists who realize that they're rather abusing the term. So it's 10 billion years old. What's going to happen to it in the future? Well, red dwarf stars, it turns out, are running on economy, and they have a trick up their sleeve. So they run very cool and burn quite slowly, but because they are able to convect all of the core where the material is undergoing nuclear fusion and mix it by convection with all of the material in the envelope, they're actually able to access all the hydrogen that they contain. So they can make use of all the fuel, whereas a much larger star like the Sun really can't do that. And so only a proportion gets used before the fusion process switches off in larger stars. But red dwarfs are able to access their entire mass. So even though the mass is lower, it lasts them a lot longer. And of course, they're burning more slowly as well at lower temperatures. And so actually, we think that a red dwarf star like this would eventually die and form a little helium white dwarf, puff off some of its outer layers maybe. But none have done so. And it's likely that a star like Barnard star might live for 500 billion years, way longer than the current age of the universe. And so no red dwarf star that has ever formed in our universe has even remotely begun to start aging and heading towards its eventual burnout. So why is Barnard star interesting then, if it's absolutely typical of these long-lived small red dwarf stars that have been around for ages? Well, it's near to us. The measurement back in the early part of the 20th century showed that it was just 6 light years away. They measure the parallax by looking at the change in position compared to the much more distant background stars of a nearby star. And you can see over the course of a year, as you orbit around the sun, you change position from one side of the sun to the other. So have a baseline of 2 times the Earth's orbital radius, so that makes 300 million kilometer baseline. That's a nice long baseline, and you can see the position of a star changing against the background. Measuring the angle that it changes very carefully, you can work out from your knowledge of trigonometry just how far away the star is likely to be. And 6 light years put it second in the table of distances, second only to Alpha Centauri. Just to give you an idea of how far 6 light years is, 1 light year is the distance traveled by light in a year, which works out at about 10 trillion kilometers or 6 trillion miles. So if you were to drive around in your car and you did 30,000 miles a year, and there happened to be an interstellar highway that went all the way to Barnard star, it would take you 200 million years to get there. Of course, that's going to be a problem if your car ran out of mechanical engine life after, say, 1 million miles. You'd need to replace the engine 6 million times or something ridiculous like that to get there. The fastest spacecraft ever launched would still take nearly 200,000 years to cross that distance. It's a long way. Here's a diagram which just shows the sun in the center and the real limit of the sun's influence, the Oort cloud out there, the final part of our solar system where the leftover building material, ice and dust forming the Oort cloud, where a lot of comets probably come from, is about 1 light year from the Earth, one light year from the sun. We go out 2 light years, 4 light years, and then we find Alpha Centauri, which is a triple star system. There's the A and B stars, which are fairly similar to the sun, and another of these red dwarfs called Proxima Centauri. And then at 6 light years, we would come across, in a different direction, Barnard star. And the other objects that are listed there with their WISE catalogue numbers, those are actually brown dwarf stars, failed stars that we've detected that are the next nearest objects after Barnard's star. Now, if you were at Barnard's star and you looked back, what would the sky look like? Well, the sun would appear in the region of the constellation of Monoceros, the unicorn, a fairly faint and obscure constellation, but we would be located within a triangle of bright stars. We would have Betelgeuse from Orion, Procyon from Canis Minor, and Sirius from Canis Major, framing the position of the sun. But the sun would be relatively faint at that position. Now, Barnard's star is also moving, and it's coming closer to us. We've mapped the movement of quite a few of the nearby stars, and it's shown on this diagram in terms of time from now and a little bit into the past, and the distance. And at the moment, Proxima Centauri and the Alpha Centauri system is the closest at just 4 light years. And then you can see the path of Barnard's star at 6 coming quite quickly towards us. And it crosses that 4 light year boundary, comes down to about 3.75. But it never quite gets closer than Proxima, because after that, Barnard's star will loop away from us as it orbits round on its trajectory around the galaxy, and Proxima will still be a little bit closer because it too is approaching us and will continue to do so for about 25 to 27,000 years, when it too starts to recede. And you can see some of the other stars on there as they approach us and move further away as we all orbit around the galaxy together. Now, all that movement results in the most interesting feature that Barnard saw, and the reason that this star bears his name. In 1916, he detected the fact that Barnard's star was hurtling across the sky. Not only do we get a parallax by looking at it over a 6-month period, but the star itself is moving relative to the background because of its rapid motion relative to us and being so close to us. 10.3 arc seconds per year is quite a substantial shift. And in fact, you'd be able to tell that with an amateur telescope just by doing some observations on the same date or thereabouts each year. You'd be able to plot its position against the background stars. So this was actually faster than any of the other stars. It became the record holder, hence it was worth naming, and that's still the case today. We've never found a nearer, faster moving one. Well, all this interest in Barnard's star and the fact that it was close to us led to us studying it to see whether there were any planets. And so we move on now to not looking at the star itself, but the possibility that there are planets orbiting around Barnard's star. Now, with it being so old and therefore not having very many of the heavy elements, it does mean that it probably was a bit short of the rocky metal materials to make up a planetary system. We think that as the universe gets dirtier, the most recent generations of stars are going to have more planet forming material available to them. And so going back 10 billion years, there is a question mark over whether there would have been any planets there at all. You might have had enough to form some pure gas planets, but trying to form a rocky core could have been difficult. So Peter van der Kamp, astronomer from Holland, tracked Barnard's star across the sky, and he tried to use a technique called astrometry, where you measure the position of the star and see if the star is wobbling back and forth, synchronized to the orbital period of an unseen companion planet. And Peter announced that he had made a discovery. In fact, he made a couple of announcements of more than one planet. The first one was of a super Jupiter planet, 1.5 times the mass of Jupiter, orbiting at about 4.4 astronomical units, an astronomical unit being the Earth-Sun distance. He also suggested there were 2 planets, one slightly larger than Jupiter and one slightly smaller than Jupiter. So I made a number of these predictions, and it was all based on looking at the data for the position on the sky. And so this data here is his position information about the right ascension, that's the longitude on the sky, and the declination, the latitude on the sky of Barnard's star. And we've drawn a wiggly line through it to indicate a sort of wobbling backwards and forwards in a sine wave. And it appears to do so about every 10 years, hence some of the numbers that Peter was able to come up with. But nobody else could ever reproduce this. This is one of those scientific arguments that went on for decades about who was right. Now, Peter sadly passed away, and he never really saw the final resolution of all of this. So I think he went to his grave in the belief that he was right. But we now know that what really happened was that we had a straight line with some experimental error there, another one here, and a third one here. And these are at 10-year intervals because the telescope was subject to maintenance at this point. And guess what? Maintenance happens every 10 years. So they took his telescope apart again. So 1962 and 1972, the telescope was slightly differently aligned when it went back together, leading to this jolt in the position. So the appearance of a sine wave is actually an artifact of the maintenance of the telescope. This was the eventual resolution of it. So sadly, none of Peter's predictions of planets came true. And that was the state until November of 2018, when this piece of news hit the headlines. It's an extract from the BBC website, and it shows the announcement of Barnard B, a planet of 3.2 times the Earth's mass, found to be orbiting round the star, Barnard's star. So one of our near neighbours suddenly announced to have a planet. Now, this is a little bit of a surprise because it is actually a super Earth, 3 and a bit times the mass of our sun. That's quite a big planet in some ways. It was orbiting around the star every 233 days, and that's an orbital period roughly the same as that of Venus going around our sun, but it was rather closer in because this is a lighter weight star that it's orbiting, so it would have been around about the orbital distance of Mercury. But nevertheless, Barnard star only puts out 1/25,000th of the heat, so this planet would have been a rather chilly minus 150 degrees C. There's a sort of diagram of its size and relative position, a schematic. Orbital distance 0.4 of an astronomical unit, orbital period 233 days, rather larger than the Earth against that much smaller star. So calculating how much heat it would release, this would have put it near the frost line where water would start to snow out, and in fact other materials like ammonia and methane would condense down as well. So it would be outside the habitable zone, but where water would exist as a liquid. It'd be jolly cold, but perhaps able to accrete quite a lot of the volatile materials at this distance. And so perhaps finding that it was a reasonably large planet sounds possible, bearing in mind what I said about Barnard star being a bit short of rock and metal, because they have the paucity of heavy metals. So various people produced some rather nice looking artist's impression here of what it might look like on Barnard B, with the red dwarf giving that red hue to the landscape. All this mountains and so forth would have been made of frozen up water and methane and carbon monoxide and things like that snowing out onto the surface. But with much stronger gravity, it should be able to hang on to quite a substantial atmosphere. At 3.2 times the mass, with a sort of typical density that we might expect for a low density world with not much metal but a reasonable amount of ice, this would be about 1.5 times the radius of the Earth. But you've got to bear in mind this detection was made not by the transit method of seeing the disk of a planet pass in front of the star, but by the radial velocity method. So it was detecting the Doppler shift wobble of the Barnard star itself. And when you do that, you are really measuring the minimum mass, because you're assuming in some ways that the maximum displacement is occurring, which would occur if the planet was orbiting across your line of sight. Whereas if it was tilted, then the mass estimate could be an underestimate. That's why it says at least 3.2 times the mass of Earth here. So very cold indeed, but the atmosphere probably bring it up a little bit from a base temperature of minus 170 up to more like minus 150. Still pretty chilly. There's another artist's impression, slightly more fanciful here, of some sort of alien vegetation on there, and the star glowing really quite bright, brighter than the full moon, but nowhere near as bright as the sun. So probably very fanciful indeed. But another factor would be that these large super-Earth bodies have a greater volume compared to their surface area. So the larger something is, the volume grows as the cube of the radius. The surface area only grows as the square of the radius. And so you get more volume compared to the area. Why does that matter? Well, you dissipate heat through the surface, through the area of the object. But the heat trapped inside is based on the bulk. It's based on the volume. And so larger bodies will have more heat trapped inside them, trying to get out through a relatively lower surface. So it's quite likely that the build-up of immense amounts of volcanoes could be one possibility for a rocky world of this size. Other possibilities are, though, that this is not so much of a rocky planet with a metal core, again, because the star doesn't have very many of those, but it's more of an ice world, perhaps with a small rocky core with a lot of heat trapped inside it and a liquid ocean underneath, rather like we find at the moons of Jupiter, such as Europa. So at the smaller end of things, quite likely to be like that, with perhaps a large amount of liquid water, maybe quite a lot of ammonia and methane. Other ices, perhaps a super Earth, we would describe that as. But if the mass was even larger, the stronger gravity would have attracted a lot of the volatile hydrogen and helium into a thick atmospheric envelope. And so we might be looking more at a mini Neptune. And so that was the state of things when I published my previous video on Barnard star. But in 2024, it all changed. It's just not true. Sorry about that. I've been exaggerating and lying to you about Barnard B. A careful look with more modern technology at the supposed signal from the rotation of the planet, from the Doppler shift of the star caused by the rotation of the planet around it, turns out to be in fact caused by the spin of the star itself. This 233-day supposed orbit of Barnard B is in fact an integer ratio multiplied by the spin of the star itself. And so the change in the Doppler shift was really being caused as an artifact of taking the star spectrum and the star spinning on its own axis. So all of that lovely speculation about Barnard B, I'm afraid, went out of the window. But in the process of analysing the data much more closely, it's been replaced by 4 new planetary candidates, B, C, D, and E. But this B is not the same as the previous B, and none of them are the same as Peter van der Kamp's planets. Gets a bit confusing, doesn't it? But here we have B, C, D, and E, and they're labelled B for the first one, C for the second one, D, and then E, in the order of discovery, not the order of distance, because if we found another planet interior, then we would have to relabel them all again, and that would get really confusing. And so the order from the planet goes D, B, C, E. Only B has actually been confirmed. The others are still hypothesized. And if we look at them, they're all actually small sub-Earth planets. So these are probably relatively modest planets like Mars or like Mercury, perhaps even as small as our moon in some cases. And the percentage size there that you have compared to the size of the planet Earth is in the documentation there on the screen in that table, with their distances all quite small fractions of an astronomical unit and their orbits going around. And again, these were all detected by this radial velocity method, looking at the blue and red shift of the light from the star, depending on where it's going towards us or away from us. Now, again, just to go back to this point, these mass estimates are actually the minimum mass of the planet, not the maximum mass. This is assuming that the orbit is causing the maximum Doppler shift from our point of view, which would mean they would need to be aligned with us in a flat plane. If there's a big tilt, it can make a huge difference. So the recent news on this is that the TESS spacecraft, the Terrestrial Planet Searcher, has gone up and looked at Barnard star and found no transit events. So we know one thing, which is that the system is not edge-on to us. So the planets are definitely bigger than the minimum estimates. What we don't know is how much bigger. If they were tipped by 60 degrees, they could be double the mass. And if they were tipped by getting on for 90 degrees, it could be a very large error indeed. So they are bigger than those minimum mass estimates, but still probably Earth or sub-Earth sized is the consensus on that one. So again, this is something that we need to follow up on. Now, I did just want to say a couple of things about the heat output of Barnard B. It's worth looking at this. These low mass red dwarf stars have a power spectrum that puts most of the light out in the infrared part of the spectrum. They're almost not warm enough to put out very much visible light at all. And the strongest color is, of course, red, and then it dips very rapidly. But most of it, and the peak indeed, is in the infrared part of the spectrum. And that means that there is quite a lot of heat coming off, even though they're not very bright. But it does mean that the Goldilocks zone, the habitable zone, is very close in. So it's possible that these close-in planets might be at a temperature that could be of interest to having water on the surface and possibly even life. But there's a downside to being so close to the star, and that is that it becomes very likely that the gravity of the star affects the rotation of the planet on its axis and brings it into what's called tidal lock, whereby one face of the planet points towards the star at all times. So 1 year for the planet equals 1 day for the planet, very much as the moon keeps one face to us because it rotates on its axis in the same time period that it takes to go round the Earth once. So it just keeps turning and turning as it goes round, keeping one face staring towards the Earth. That tidal lock is caused by gravity. It's caused by the fact that the planet is pulling back on the star and trying to raise tides on the surface of the star, or in the case of the moon, the tides of the oceans. And that acts as a friction brake, which pulls the planet into alignment and forces this tidal lock situation. Now, if that happens, you will get one side of your planet very, very hot and one side very, very cold. But it could mean that there are temperate zones along the day-night boundary where the sunlight is coming in obliquely. It might make the weather pretty weird, but it's definitely going to create a range of temperatures on these planets. So it's definitely a place that we need to study more closely. And we're going to do that because the James Webb Space Telescope has studying Barnard B and its possible companions as one of the things that is on its list of things to go and image and attempt to measure much more about them directly. Now, Barnard's star is also featured because the British Interplanetary Society had the idea of it being a really good target for an interstellar mission, and that was called Daedalus Icarus. So it's a two-stage rocket, but a nuclear rocket using nuclear fusion that would accelerate to 12% of the speed of light and try and get to Barnard's star in 50 years. Now, this was proposed back in the Apollo days, before Apollo had even got to the moon. And there's an Apollo Saturn V stood next to Daedalus Icarus, just for comparison of the size there in terms of the artist's impression. The two stages of the interstellar probe would have been powered by a fusion engine. Now, no one's built a fusion engine yet, but it ought to be possible. We ought to be able to inject hydrogen, cause nuclear fusion, generate heat, and have the resulting exhaust accelerate us to very, very high speeds indeed, much more efficient than an atomic engine using uranium, because the uranium's very heavy, and certainly way better than any chemical rocket could ever achieve. So it's possible that such a thing could accelerate a probe up to the speed of light. This would have been two stages, Daedalus for the base, Icarus for the top. And it would have been so large that it would have had to have been constructed in orbit. So maybe one day we will get round to building something a bit like this and be able to fly a probe, even if we don't fly humans, off on a 50-year trip to Barnard's star and get up close and personal and have a really good look at all of those planets that there are in that solar system just 6 light years away. So thanks very much for listening to that, and I hope you've enjoyed the update. Bye for now.